welcome to lecture number 30, fuzzy sets, logic and systems and applications. So, in this lecture we will discuss the operations on crisp and fuzzy relations, and of course, as I already mentioned in my previous lecture that fuzzy relation set is also a fuzzy set. So, in the previous class I mentioned that related to this fuzzy relation set, we have the operations as union, intersection, complement and containment. And let us first understand what is the union of relations. So, let us first take the union of crisp set. So, if we have two crisp sets R and S, and these sets are the relation sets. So, we have, in other words, we can say the R and S be the crisp relations defined on the space capital X cross Y, and then the union is defined by another crisp set, that is T, which is equal to R union S. You can see here, and this T is said to be the union of R and S. And here this T set will contain the ordered pairs as elements in this set. So, for every ordered pair x and y belonging to R, or x comma y, that is again an ordered pair which is belonging into another relation capital S. So, then what is happening to the elements of the set T. So, here also for every x y, that is the ordered pairs that is belonging into fuzzy relations T, such that for every ordered pair x y is belonging into x cross y. So, this was basically for the crisp relation sets R and S, and then we had out of the union we have another fuzzy set which is T, which is coming out of the union of R and S. Now, let us discuss the union of fuzzy relations. So, as we have seen earlier also that there is a difference in crisp and fuzzy relation, and what is the difference? Difference here is that here in fuzzy relation, and as of course, I have already told you that fuzzy relation is a fuzzy set finally. So, the fuzzy relation set will have its corresponding membership values. So, that is what is the difference here. Other than this, there is no difference. So, in fuzzy relation set, we will have, apart from the ordered pairs, we will have the corresponding membership values. Here we have the ordered pair, and then we have the mu t of x comma y, means the corresponding membership value. So, this way we have the union of fuzzy relations, and these are the fuzzy relation sets, and as I have already mentioned that these R and S basically are fuzzy relations, but these are fuzzy sets. Now, how to get this mu capital T of x comma y, means mu capital T of the ordered pair, means the corresponding membership value. So, how to get that in case of union? So, in case of union, you see here mu t of x comma y, we are applying the max criteria. We take the max of mu r x y and then mu s x y. So, this means what? This means you see here we take the corresponding membership value which is present in the fuzzy relation set R and then fuzzy relation set S, and when we are taking the union of it, the R and S, then we take the max of these two membership values and then we term this as the mu capital T of x comma y. So, this way we find the corresponding membership value corresponding to the order pair. And of course, it is needless to mention here that for every x y belonging into capital S, such that for every x y belonging into capital X cross capital Y. And this is because R and S are already defined in the space capital X cross Y, because R and S are the fuzzy relations set. So, when we talk of the intersection of crisp relations, we will go similar on similar lines. You see that the when we talk of crisp relations, so you see here for crisp relation you take the intersection, and when you take the intersection you take only the common elements, right. So, T is said to be the intersection of R and S if for every x y that is belonging into R and belonging into capital S, and the resulting set here will be the x y that will belong into the capital T, that is the order pair element which will belong into the capital T, which is the outcome of the intersection of capital R and capital S. Now, let us understand the intersection of fuzzy relations with respect to here again the fuzzy relations. We have to have an additional term here in the set. So, T set here will have the associated membership values, which was not there in the crisp set, and you know why. I have already explained couple of times that here in fuzzy set we have to have this mu T x y are the associated membership values associated, otherwise you know we may not be aware, we may not be knowing as to with what membership value a particular element is existing in the fuzzy set. So, let us now quickly define this. So, T here is the fuzzy set, and here the element will be the x comma y, which is ordered pair, and then its corresponding membership value mu T of x y, and let us see as to how we can compute mu T of x comma y. So, here instead of max as in the previous case where we were taking union, here we, since we are having we are interested in finding the intersection. So, we take the min of the two membership values. So, when we are taking the intersection of fuzzy relations, we use the min criteria. So, when we take the min of these two membership values, the resulting value will be termed as mu T of x comma y, and which is coming because of the intersection of R and S fuzzy relations set. So, it is again needless to mention here that for every x comma y which is belonging into R and S, and then this x and x comma y will also be coming from x cross y. So, capital R, capital S both are the fuzzy relation set, and this is again drawn from capital X cross capital Y, which is the Cartesian product space. So, now coming to complement of crisp relation. So, as we have seen union and intersection, here the complement of crisp relation we will first discuss, and then we will go to the complement of fuzzy relations. So, as we have already seen in the case of crisp set, how to find the complement of any crisp set, here also since we are discussing about the crisp relation. So, crisp relation again is a crisp set. So, let R be the crisp relation defined on the space capital X cross Y, then the complement of relation capital R is defined as if the ordered pair x comma y ordered pair element which is not belonging into R, then x comma y will belong into the R bar. R bar is the complement set, and this complement of relation R will be basically the collection of all the ordered pairs elements like x comma y, such that for every x comma y is not belonging into the set R, that is the crisp relation set R that we have taken. So, it is very easy to understand that we will include all the ordered pairs which are not there in capital R, and all the ordered pairs means all the ordered pairs that are existing in the Cartesian product space. So, this way we have understood the complement of crisp relation. Now, let us go to the complement of fuzzy relation. So, as I have already mentioned that here the difference is that we include the membership values along with the ordered pair elements. So, here we have mu r bar of x comma y. So, this complement of relation R is represented by R bar, which is here you see. So, this is basically the collection of this is equal to the set, which is collection of all the ordered pair elements, and these elements are those elements which are not existing in the set that we have taken, but these are existing in the Cartesian product space capital X cross capital Y, and this along with the membership values. So, how to find this membership value mu r bar of x y, see here. So, this is very easy, we here take a very basic complement, otherwise you can take other complements also, like we have done in previous lectures. So, we are discussing only the basic complement here, which is 1 minus mu r of x comma y. So, if we apply this, we will compute the mu r bar of x comma y. So, this way it is very easy to compute the complement of fuzzy relation. Now, coming over to the containment of crisp relation. So, if we have any two fuzzy sets capital R and capital S. So, here let us first, before we move to fuzzy sets, let us first understand the crisp relation, then we see the transition from crisp relation to fuzzy relation. So, if we have capital R and capital S as crisp relation set, so then the containment is defined by the set which is, let us say, capital T, and this is equal to R, which is a subset of S. So, R is contained in S if for every x comma y, which is the ordered pair element belonging into capital R, and x comma y again belonging into capital S. So, this way then capital R of x comma y is less than or equal to S of x comma y for every ordered pairs that is belonging into the Cartesian space, that is capital X cross capital Y. So, let us now move to the containment of fuzzy relation. So, here as I just mentioned initially, so if we have R and S as fuzzy relation sets, how to represent the containment here. So, containment, if we have the containment, right, like R is contained in S. So, that is possible only when if for every ordered pair elements x comma y is belonging into R and S, and then mu r of x comma y will be less than or equal to mu x and x comma y, and this is again for every ordered pair elements x and y belonging into the space of capital X cross y. So, this can be very well understood by taking one example here, and in this example here we have taken two crisp sets A and B. So, let us first understand that here we have two crisp sets A and B, and the universe of discourse of both the sets like capital X and Y are also the same. So, let us first find the Cartesian product of A and B, that means A cross B. So, as we have already seen that how we can get the Cartesian product of crisp set A and B. So, we can very easily find the Cartesian product of two crisp sets A and B. You can see here. So, we have all these elements, it is very easy to quickly find, and this way when we have found this, then now let us go to the relation matrix. So, let us put some condition, as I have already mentioned in case of crisp sets, in case of crisp relations. So, here we have the complete population, we have the ordered pair elements in A cross B. So, now let us put some condition here, and the condition that we are putting here is the first element is greater or equal to the second element. So, if we put this condition here, that is this case, and let this be represented by Q4. So, Q here is for relation. So, Q4 of A comma B here. So, this represents the relation in crisp set A comma B. So, we have collected here all those elements which follow the condition that has been stated here, like the first element is greater or equal to the second element, like 2 2, 3 2, 3 3, 4 2, 4 3, 4 4, all these have been included. And the same can be represented by the relational matrix. So, we can see that we have few ones and few zeros. So, the elements that are existing, the pairs that are existing here, like from A 2 as the element and from B 2 also as the element, both are forming the ordered pair in Q4 A comma B. So, that is why since this is existing here, so that is why 1 has been put here as one of the elements of the relation matrix. Similarly, here 3 2 is also existing, then 4 2 is also existing, and then 3 3 is existing, 4 3 is existing, and then 4 4 is also existing in the Q4 A comma B set. No other elements are existing. So, that is why other elements have been put as 0. Now, when we have this Q4 A comma B, since this is a crisp set as the relation set. So, if we are interested in finding the complement of this relation set, we can quickly see as to how we can find that. So, if it is the complement relation, so we represent this by the Q4 bar, you can see here. So, this is Q4 bar of AB, and this is equal to a relational representation here. We see that we change 1 into 0 and 0 into 1, means those elements which were not present in Q4 A comma B are present here in this set Q4 bar of A comma B. So, this way we find the complement of a crisp relation. Now, another relation set, that is Q5 A comma B, such that the second element is greater than or equal to the first element. So, on the same lines we can find this set here, you can just try, and then we find the relational matrix here as I have described in the previous case, and if we are interested in finding the complement, we can quickly get the complement by just changing 1 to 0 and 0 to 1. So, this way the complement is found. Now, as a fourth case here, we are interested in finding the union of Q4 and Q5, and then the intersection of Q4 and Q5. So, we have Q4 here, Q4 relation set, the crisp relation set, and then we have Q5 as the another crisp relation set. So, we have two crisp relation sets. Let us now find the union first. So, when we take the union, you see here we again see that we have those elements which are present in the set Q4 A comma B, and again those elements which are present in Q5 A comma B, you see. So, all those elements are being accounted. So, this way all the elements are present here. So, Q4 Q5 we look at the relational matrix, and then we keep all ones which are in both the relation sets that are Q4, Q5. Now, when we are taking the intersection, so in intersection we only take the common ones. So, if we see here in Q4 AB, these ones are present in Q4 AB and these ones are also present in Q5 A comma B. No other ones are present in both the relations matrix Q4 and Q5. So, that is why only these are kept. So, this is how we get the crisp relation operations done, and similarly if we are interested applying the operations on fuzzy relation sets. So, we can also do that, and as we have already seen that we have fuzzy relation set like this. If we have an R fuzzy relation set and another fuzzy relation set S. So, we can represent this R fuzzy relation set like this and S fuzzy relation set like this, and if we are interested in the applying the operations on the fuzzy relations, these R and S sets. So, let us now see as to how we can move ahead. So, here basically our intention is to find the union of these two fuzzy relations. So, R is the fuzzy relation, I am writing here set, and S also. So, both of these are the fuzzy relation sets. Now, please recall as to how we can find the union of these two fuzzy relation sets. So, if we recall, we see that we have fuzzy relation set which is out of the union of the two R and S, and the membership values we represent this by mu t of x comma y. So, this way we represent, and when we are taking the union here. So, in union what we do? We recall that we have applied the max criteria and we take the max of the membership values corresponding to the ordered paired elements. So, here we see that when we take the union. So, we see that we have 0.3 here, we have 0.3 here, and if we take the union we use the max. So, here we apply max criteria, and this way we get the mu t of x y. So, all the elements of mu t can be computed by applying max very quickly, and all these have been associated along with the generic variable values as the ordered pair element like x comma y in the resulting fuzzy relation set T. So, this was the union when we take the intersection. So, in intersection instead of max we take the minimum, and when we take minimum, let us say we take this element and this element, and corresponding to the ordered pair values we take min, we are getting here 0.1. So, this is nothing but the mu is as mu s x y, and then this is mu r x y, and this is here is mu t x y. So, all these corresponding values can be very easily computed, and this way we find the intersection of two fuzzy relations. And then when it comes to complement of fuzzy relation, then we apply this criteria. We simply subtract the corresponding membership values from 1, which is again the basic complement, and if you wish you can apply the other complements that I have already taught in the previous lectures. So, if you want to get the complement of fuzzy relation capital R set, so you can quickly write the fuzzy relation R set here, and then how to get this R bar is just subtract all the corresponding elements here. Corresponding elements means you see these are the membership values and these membership values are subtracted from 1. So, when you subtract this value from 1, so that means that we are subtracting 0.3 from 1 and this is going to give us the value which is 0.7. So, likewise all other values of the complement of fuzzy relation set we get, and this way we manage to get the complement of any fuzzy relation set. Similarly, we can get the complement of fuzzy relation set S, and which is represented by S bar. Here also if we see, let us say we take 0.1 and the corresponding the element in S bar will be 0.9, because if I subtract 0.1 from 1 we are going to get 0.9. So, this is how we get the corresponding membership value, which is the membership value of the complement of the fuzzy relation set. So, this is how we get the these operations applied on fuzzy relations. And now, when it comes to the containment for fuzzy relations, so similarly if fuzzy relation set R is subset of S, then you see if this is the case, then mu R x y will be less than or equal to mu x of x y, and this is for every x belonging into capital X and y belonging into capital Y. So, if we have two sets you see here, so if with these two fuzzy relation sets that we have, if we put this condition here, so we find that R is not a subset of S, because this condition is not satisfied. That means, all the membership values of set R is not less than or equal to the membership values of relation set S. So, that is why we can say that R is not a subset of S. So, this is mentioned over here. So, therefore, we can say R is not contained in S. So, this way we have seen that we have understood operations, the complement, intersection, union, containment with respect to crisp sets and fuzzy sets in today's lecture. And not only fuzzy sets, but I would say we have studied these operations on the fuzzy relation set. Of course, the fuzzy relation set is also a fuzzy set. We would like to stop here, and in the next lecture we will discuss the following: the projection of fuzzy relation, cylindrical extension of projection, properties of fuzzy relations. Thank you.